Hey guys, in this video, I will shortly talk about Miller-Rabin Primality Test. Before watching the video, you need some basic knowledge about the calculation of modular arithmetic. This is our first question: how to decide whether a given number is a prime? The simplest way is just to try to factorize the number, but this method will takes the square root of n steps. So, what happens when the number has hundreds of digits? Of course, the former method can't apply to this case. But we can apply Miller-Rabin Primality Test to get the answer in each few steps. This is the importance of Miller-Rabin Primality Test. It is an important algorithm for computers to judge whether a large number is a prime. It reduces the time complexity from O(n) to the power of k to OK times log n to the power of 3. Before introducing Miller-Rabin Primality Test, you should first know about Fermat Little Theorem. Fermat Little Theorem states that for a given number prime p, the following congruence always exists while the greatest common divisor between a and p equals 1. Let me prove it. Let S be all the congruence classes of p except 0 modulo p. Then we can multiply each element in S by A, which is co-prime to P. We then get a new set, A to A, 3A until P minus 1A modulo P. Let W equals the new set. We then should prove S equals W. To prove S equals W, we need to prove the following claim. Each pair of elements in W is congruent. Prove by contradiction. If two elements in W are congruent, let them be NA and MA. We then get the following congruence. NA is congruent to MA modulo P. Since A is co-prime to P, we can divide the congruence by A and then get N is congruent to M modulo P. However, since N and M are all in the set S, they are from different congruence classes. We complete our proof of the claim. Therefore, we have p minus 1 congruence classes in W except 0 modulo p, which is also the definition of S. So far, we have completed the proof that S equals W. Since S equals W, the multiple of their elements should be the same, and we then get a factorial of p minus 1 is congruent to factorial of p minus 1 times a to the power of p minus 1 modulo p. Because p is a prime, we can divide the congruence by factorial of p minus 1 and then get what we want. So far, we have completed the proof of Fermat Little Theorem. And then I will talk about the concept of witness. According to Fermat Little Theorem, for every prime number p, we have this one. So if the congruence doesn't hold, the number p isn't a prime. In this case, we call the number a witness. However, what can be inferred from the congruence? Can we say that p is a prime? Apparently not. Even if the congruence holds for every number a between 1 and p minus 1, the number p can still be a composite number. For example, the number 561 has these characteristics, but 561 is a composite number. We call this kind of number Carmichael number. Miller-Rabin Primality Test. Since we all know that the solutions to x squared equals 1 are 1 and minus 1, we can easily come up with the idea that the solutions to x squared is congruent to 1 modulo p are 1 modulo p and minus 1 modulo p. According to Fermat Little Theorem, we get x squared is congruent to 1, which is congruent to a to the power of p minus 1 modulo p. We then get a to the power of p minus 1 over 2 is congruent to 1 or minus 1 modulo p, as long as p minus 1 is divisible by 2. If it is congruent to 1, we have this new congruence. A to the power of p minus 1 over 4 is congruent to 1 or minus 1 modulo p, as long as p minus 1 over 2 is still divisible by 2. We notice that how many times can p minus 1 be divided by 2 is important. Therefore, we let p minus 1 be 2 to the power of k times q, in which q is an odd number. Now we can discuss the value of a to the power of 2 to the power of I times q modulo p. We start from the situation where I equals 0. We have a to the power of q modulo p. There are two cases. It is congruent to 1 modulo p. In this case, all the value of this congruence is 1 modulo p. The second case is when the condition 1 doesn't exist. In this case, there must be the number j between 1 and k minus 1, so that a to the power of 2 to the power of j times q is congruent to minus 1 modulo p. Proof by contradiction. Because p is a prime, we have a to the power of 2 to the power of k times q is congruent to 1 modulo p. As we discussed earlier, there exists this one. Since there's no j, that will let this one exist. So a to the power of 2 to the power of k minus 1 times q must be 1. Repeat this process until the power of 2 reduces to 0. We then will have a to the power of q is congruent to 1 modulo p. But that congruence doesn't hold. Here we complete our proof that there exists a j that will let the following congruence exist. Therefore, we know that if a number p is a prime and p minus 1 equals 2 to the power of k times q, one of the following conditions must hold. Return to our discussion about witness. If the number n doesn't meet one of the conditions, n must be a composite number. We call the number a that doesn't meet the conditions witness. Miller-Rabin Primality Test ensures that if n is a composite number, at least 3/4 of the numbers in 2 to n minus 1 must be the witness to n. However, this claim is very hard to prove, so I won't introduce it in this video. So far, I have completed the introduction of Miller-Rabin Primality Test. I will need some practice. For some composite numbers, you can try to find the value of a to the power of n minus 1 modulo n. You can also try this one for 561, a canonical number. You can also try to identify the characteristic of canonical numbers. Thank you for listening.